Hello everyone. My name is Varsha Felsi and I'm an assistant professor in the Department of Space Science, St. Albert's College, Ernakulam. So today we will be discussing about active galactic nuclei. Before getting into what is an active galactic nuclei, let us recollect what we know about galaxies. Galaxies are actually these sprawling systems of gas, dust, billions of stars, dark matter, and all of this held together by gravity. And most of these are consisting of about 10 raised to 9 solar mass to 10 raised to 12 solar mass. So these are huge entities, and most of these are said to harbor a supermassive black hole at their center. Or even our galaxy Milky Way, it has a supermassive black hole at the center, and it is known as Sagittarius A. Galaxies can be broadly classified into spiral galaxies, elliptical galaxies, irregular galaxies, and lenticular galaxies. So this here we can see the Hubble tuning fork diagram, which is used for the classification of galaxies. So galaxies are classified according to their morphology, their shape. So here we can see these are elliptical galaxies are elliptical in shape, and then the tuning fork actually has two arms, and the arms consist of the spiral galaxies. The upper half is the normal galaxies, and the lower half we can see they are barred spirals. So it's actually spirals with a bar in the center. And then there are lenticular galaxies and irregular galaxies without any particular shape. So our galaxy Milky Way is a spiral galaxy, and it is a huge galaxy. So as we said earlier, most of these galaxies has a supermassive black hole at its center. But the presence of the supermassive black hole does not lead to a significant increase in the luminosity. So if we are talking about the normal galaxies, the total luminosity is the sum of the luminosities of individual stars taken together. But this is not the case in all of these galaxies, because there is this small class of galaxies known as active galaxies, which only constitute about 1 to 2% of whole of the galaxies taken together. So in these, this is not the case. So here the total luminosity is not what we get by summing up all the individual luminosities. So these are what we call active galaxies, and they have an active galactic nuclei at the center. Or in other words, the supermassive black hole at the center is accreting mass from its vicinity. So these are what we call AGNs, or active galactic nuclei. So AGNs actually have a nearly stellar shape on photographic plate, and for the same reason, they has been called, like in earlier time, people used to think that they are actually stars, and for the same name, for the same reason, people used to call them quasars. Quasars means quasi-star, so it's not exactly a star, but it looked like a star. And these can be detected in throughout the electromagnetic spectrum. And as we said earlier, they have very high luminosities when compared to the normal galaxies. And the center black hole is accreting mass in large amount, leading to this increase in luminosity. And this luminosity is actually highly variable. So we are not getting a stable luminosity, and this variability can range from time scales from minutes to hours. And using this variability, we can actually infer about the size of the AGN. So these are some of the values that we use. These are some of the values for a typical AGN, and the size is almost of the order of 10 raised to 13 centimeter, and the accretion rate, the rate at which this accretion is taking place, is of the order of 10 solar 10 solar mass per year, and the Eddington luminosity is of the order of 10 raised to 38. So there are different types of AGN. Like if we are looking at here, we can see there are blazars, quasars, Seyfert galaxies, radio galaxies, and there are different types of AGNs. But according to this model known as the unified model, all of these AGNs can be actually considered as a single entity being observed under different conditions. So here we can see the blazars. So we are looking at the blazars at we are directly looking at the jet of the blazer. So the angle between us and the jet is 0 degree. And with quasars, there is a small angle, like about 30. It's not zero, but it's not that large. And then Seyfert galaxies, and then comes radio galaxies. So we are looking at the radio galaxies about 90 degrees. So here we can see that. Here we can see how the unified model actually incorporates everything under the same umbrella. Okay, so when we are coming to the structure of an AGN, a typical AGN has a supermassive black hole in the center, and then there is the accretion disk, the region from which the accretion is taking place, and then beyond this or above this accretion disk, there is a broad line region. So these consist of heavily ionized clouds, and beyond this BLR or broad line region, we have NLR or narrow line region, which consist of heavy ionized clouds. And then the most interesting thing about AGNs is that they have radio jets, and the emission from this jet is actually boosted in the direction of the motion, and it is collimated by the combination of intense magnetic fields and powerful winds from the accretion disk. And then at last, here we can see this is the torus, which surrounds the accretion disk. So we have seen what an AGN is, its characteristics, and the different types of AGN, how the unified model brings them together into a single entity. And then we have also seen the structure of a typical AGN. And now the real question is, why are we studying these AGN? Yes, they are really interesting objects, but the real reason is that these are probable sources of cosmic rays. And cosmic rays are these particles that are being showering upon us constantly from all directions. And these mostly consist of charged particles like protons, electrons, positrons, and all. And for the same reason, when they are traveling through space, they get deflected by magnetic field, and hence it's hard for us to discern their sources. So one of the most probable sources of cosmic rays which are coming from which are extragalactic cosmic rays is said to be AGN. And this is actually Hillas plot, which shows the probable sources of cosmic rays. It gives a condition for something to be like the source of a cosmic ray, source of cosmic rays actually. So here we can say that AGN clearly fits in this. The energy density of extragalactic cosmic rays is exactly same as it tallies with the energy density of all the AGNs taken together. And another reason is that these are highly redshifted objects. So we are looking at these objects which are highly redshifted, and hence they will tell us about how things has evolved and how the universe has been evolving. So that is another advantage. And we can also study about extragalactic background light using AGNs, and then we use them to study about the emission mechanisms at very high energies, and thus we can get a better understanding about relativistic conditions. So thus we have learned about what an AGN is and what are its characteristics, its structure, and we have also looked at what are some of the reasons for studying AGN. So that's all for today. Thank you.